So we are going to start the program. Program start गर्न चाहिँ फर्स्टमा चाहिँ हामी यो चेयरिङको सेसन गर्दैछौँ. चेयरिङको सेसनमा चाहिँ फर्स्ट I would like to request campus chief, Southwestern State College, Dr. Rajendra Kesi, to please come and have a seat. So today with us we have Dr. Henry Troop. So I would like to request him to have his chair and the chief guest for the program. I would like to request Hari Singh Kesi sir, Assistant Campus Chief, Southwestern State College, to have his chair. Similarly, with us we have Mrs. Sarita Satya Pradhan, International Relations Coordinator, Southwestern State College. I would like to request Mr. Suresh Bhattarai, Chairperson NASO, to have his seat, please. Similarly, I would like to request Mr. Madhav Marahata, Board of Directors, Southwestern State College, to have a seat, please. Similarly, I would like to request Vijay Sagar Pradhan, Board of Directors, Southwestern State College, to have a seat. Similarly, with us we have Dr. Nama Budatoki. I would like to request him to have his seat. So without much ado, we are going to start our program. Although हामी चाहिँ 20 मिनेट ढिलो भइसकेका छौँ. So I would like to request Mr. Suresh Bhattarai, Chairman, Nepal Astronomical Society, NASO, for his welcome speech.
Thank you, Manisha. Respected chair, everyone, guests on the dais, and especially the students in front who are excited to get a lecture by Dr. Henry today. So we are a little bit behind the schedule as planned. So I would like to welcome you to this grand event to discuss about the historic mission to Pluto and beyond, New Horizons by NASA. So I hope you will get a lot of good information from this event, and which will be helpful for your science career in the future. With this note, I would like to welcome you once again on dais and all the students and teachers sitting over there. Welcome to this show. Thank you.
Thank you, Mr. Suresh Bhattarai. Now I would like to request Dr. Rajendra Kesi, Campus Chief, Southwestern State College, for his remarks.
Thank you, madam. Our senior scientist, Dr. Henry from PSI USA, Chairman of NASO, Suresh Bhattarai, and all delegates from different institutions, namaste and very good afternoon. The art and science of asking questions is the source of all knowledge. Scientists are an interesting types of people. They are creative, adventurous, critical, and realistic. This may not be initial subset of people. However, think for an instance of the motivation required to tackle the great intellectual challenges of our time. Scientists are driven by constant, therefore, Dr. Henry is here in Nepal, Southwestern State College. Now, I would like to tell about management. The teams that regularly perform at the highest levels of able to come together and be unified across the college, staffs, promoter, management, and ownership. When everyone is one of the place. Trust, develop, and teams can grow up and succeed together. There are some things you can't learn at any university, but you can in Southwestern State College. Expect for one, the University of Life, the only one college where everyone is long-lasting students in Southwestern State College. So management must know how I understand, learn at the fast and the world is changing. Therefore, Southwestern State College is here. Now I would like to tell about who we are, what we are doing. Our motto is, the speech make the masters. Our vision, we are focusing our service and quality as a world-class facilities and to produce the entrepreneurs. Our mission, articulate the outstanding entrepreneurs, researcher and knowledge transfer. Our major concern is work-based learning, need-based education, and resource-based curriculum. If we look at our history of Southwestern State College, we established in 2010. At that time, we had only 149 students and 25 staffs. Right now, we have more than 3,300 students and more than 400 staffs over here. Right now, we have one land and building around 100,044 square feet. You can see over here, it is well equipped, well infrastructure like international standard. If you go in any country in the world, you will like this type of infrastructure. Our main motto is, if the student go anywhere in the world, they should be used to like us, because not new things anywhere in the world. And right now we are working national level program with Higher Secondary Education Board, Ministry of Education, Tribhuvan University, Purvanchal University, Management Association of Nepal, Nepal PhD Association nationally. If we look at international level, Mewar University, India, Dr. K.N. Modi University, India, Geddes University, Turkey, Central University, Norway, American University, and many more European universities. Therefore, we completed our 7 years. We got lot of develops in the education and other areas. We have two types of education system. One credit system, other one non-credit system. Credit system, we follow the rules and regulation, terms and conditions according to Nepal government as a government curriculum. In other hand, we are focusing on yoga class, seminar, extra activities, smart classes. We are doing national, international exposure. We are doing a lot of things. Therefore, this time is very short. I can define a lot of things over here. Please visit our website, and physically you are here. You can see a lot of things in our website also. Finally, thank you so much, all delegates, all our students and delegates. Thank you so much for your time and your valuable time. Thank you so much.
Thank you, Dr. Rajendra Keshi. Now we are heading toward the most important part of today's program. A talk by our chief guest, Henry Thurber himself. Before he starts, I would would like to read out a short bio on him. Dr. Henry Thorpe. Dr. Thorpe is a senior scientist with the Planetary Science Institute in Tucson, Arizona, USA. He received a PhD in planetary science from the University of Colorado, USA in 2000. He is involved with the New Horizons mission to Pluto, working with the visible air spectrometer, RAF team, Dr. Tim. Dr. Thorpe has been a member of science team for NASA's New Horizons mission since 2003 and was involved in its historical flyby of Pluto on July 14, 2015. He is responsible for writing award-winning software for operation planning. He has also been involved with the Cassini mission's Imagine team in the data acquisition and analysis of ring studies in particular. He is a frequent consultant to the US, NASA, and the National Science Foundation. While working at NASA, he managed two of NASA's major scientific research programs. While living in Africa, Dr. Thorpe worked extensively with rural schools, helping to develop their science programs and inspire the next generation of leaders. He has presented more than 100 lectures for science festivals, planetariums, school groups, and public events across USA, Mexico, and Africa. Dr. Thorpe's work has been featured in Science, Nature, Time, The Washington Post, on the History Channel, and National Geographic Channel. And with its permission, he will be in Nepal television tomorrow. So let me read the abstract. NASA's New Horizons mission to Pluto and beyond. After a 9-year journey through the solar system, astronomers visited Pluto for the first time in July 2015, using a robotic NASA spacecraft called New Horizons. Despite being a tiny, icy body far from the sun's warmth, New Horizons found Pluto's surface to be astonishingly young and active, showing a diverse variety of geology never seen in the solar system. The New Horizons science team member, Dr. Henry Thorpe, will tell the story of this NASA spacecraft mission, from its development and construction to launch in 2006, to its successful encounter with Pluto, and plans for a flyby in the Kuiper Belt on 1st January 2019. So, Thorpe, the floor is yours.
Namaste, and thank you so much for having me in Nepal. It's such a pleasure to give this seminar in Nepal. It's such a pleasure to be here. Thank you so much. Just a little bit about what I'm doing and what sort of astronomy I do. First of all, I'm wearing a suit here. I'm not wearing a space suit. I'm not an astronaut. I'm an astronomer. And so astronomers spend their time analyzing data that's on the ground using telescopes and using computers. So I study the planets. I use telescopes. I spend most of my time reading and writing papers, doing research, using computers, debugging software, talking with colleagues and things like that. I have not been into space, and I probably won't go into space, but so that's why I'm an astronomer and not an astronaut. What I do get to do is I do get to use a lot of telescopes around the world. I get to use a lot of spacecraft around the world. Maybe turn these lights off or dim them a little bit so we can see the pictures more. And I get to do research using these spacecraft, using these telescopes to study the origin and evolution of the solar system. And so it's controlling me here. So you don't need to control it there. So I did my undergraduate in the United States, studying physics. Then I did an MSc in astronomy at the University of Colorado and a PhD in astronomy. And what was really exciting and what was really fun about doing the PhD and MSc, it sounds like a lot of school because it's going to school for 9 years, but as many of you know from being students, it's kind of fun. I really enjoy being a student because I'm curious, because I enjoy learning. Many students who are in the US, almost all students in the US who are studying this science, they receive a bursary and they receive a small stipend so they can continue their studies without paying tuition. And that applies to students from the US and also international students who come to the US for their studies. So for those of you who are at the top of your class, who are very good students, who are motivated, who are studying science or engineering or other areas like this, there's a lot of opportunities for you in the US or in Europe or in other countries to continue your study. So I encourage you to look at those possibilities. So I'm going to talk about Pluto. In order to talk about Pluto, I'm going to put us in the context of where we are. So this is the Milky Way Galaxy. The Milky Way Galaxy is the galaxy that we are in. Now this is not a picture of the Milky Way, this is a picture of somebody else's galaxy, because we can't take a picture of our galaxy because we're right in the middle of it. But if we could take a picture of it, you would see that we're in the middle of it here, where the red dot is circled. We are one star among approximately 100 billion stars in this galaxy. Now it's the solar system. The solar system is called this because there's one sun in the solar system. The sun is the center of the solar system. What's the first planet after the sun? Mercury. What's after that? Venus, then Earth, and then excellent, excellent. You're doing very good. So we call these the. You've learned this in like standard 2, right? Well, you haven't forgotten it yet. That's good. So we call these planets the inner planets, the rocky planets. And we call these because they're basically all made of rock. If you go to Mercury, Venus, or Mars, you can pick up a chunk of rock. They're all made of the same kinds of things that the Earth is made of. Now, what's the next planet after that? Jupiter, right? After that, we have Saturn, Uranus, Neptune. Let's see. I'll get it. There we go. There's Jupiter, Saturn. Come on here, Uranus, and Neptune. We call these planets the gas giant planets, and that's because these planets are the ones which are mostly made of hydrogen gas, hydrogen and helium. And so there's not a core. You can't go and collect rocks from the surface of them, but gravity holds everything together in the universe. And so if you have a big cloud of gas, it holds together this cloud of gas just like it would hold together the Earth. And so these planets we call the gas giant planets. Now the main difference as you get further out in the solar system is that it gets colder. So the sun is at the center of the solar system, the sun's over here, and you're right next to the sun. It's very, very hot. You know, you're sweating and you're just baking right here. As you get further and further away from the solar system, or from the sun, it's a nice relaxing temperature, and then you get further and further away. And, now you need your your big North Face jacket to stay warm out here because it's really, really cold as you get further and further out. So what do we get to after we get to the gas giant planets? We get to the ice bodies. These are things like Pluto and the other bodies in what we call the Kuiper Belt. And it's colder and colder in the outer part of the solar system because we're further and further from the sun. And so this is essentially a third class of planets called the Icy Planets. And so we have things made out of rocks, things made out of gas, and things made out of ice as we go out into the solar system. Now, people have been studying the solar system for a long time. You don't need a telescope to, maybe we can just keep those lights down. Just keep them down. It's all right. You don't need just keep them there. Thank you. We don't need a telescope to study the solar system. People have been studying the solar system for thousands of years. I live in Bombay, in Bandra, and from my flat in Bombay, you can see much of the solar system right here. In fact, you can see the sun coming up here. This is about 2 years ago that I took this picture from the top of my flat. You can see the sun, moon, Venus, Mercury, Earth, Mars, Jupiter, and Saturn. You can see almost all these planets in a line on one special night. We've been looking at these planets for thousands of years. Now, you can't see Uranus or Neptune or the asteroids or Pluto because they're too faint to see. But you can see all the other things with your naked eye with no telescope required. You can see those from Kathmandu or from any city in the world. So let's look at Pluto. Let me put the context of Pluto in history here. So in 1874, there was a French astronomer named Urbain Le Verrier, and he was looking at the position of Uranus. And he knew that the position of Uranus, all the planets are supposed to follow what's called an ellipse. It's essentially a lopsided circle in the sky. And he was looking at the position of Uranus, and he said, well, Uranus is not following a circle exactly like it should, not following this ellipse. And he studied its position, and he thought that Uranus was being pulled around by another unknown planet. So there was another planet which was near Uranus, which was changing its position. And so he studied Uranus, and he said, well, you know what, Uranus should be here, but it's over here. I think there must be another body which is changing its position, and that body must be, and he did his calculations, and he said, there must be another planet right here. And so he called up his friend, he got a telescope, and they looked out there, and the next night, guess what they found? They found Neptune the very next night. So this is one of the most amazing predictions in all of astronomy, where they predicted Neptune, and they found it. They discovered it the very next night. Now fast forward to the 1920s here. Let's see, can we have the next slide there? This is not forward. Can we have the next slide? Yes, right there, thank you. So 1905, Percival Lowell started a search for planet X. Percival Lowell was searching for another planet. He was looking at the position of Neptune, and he said, you know, Neptune isn't following the ellipse which it's supposed to follow. I think there's something which is tugging it around. So he did his studies up there, and he said, I think there must be another planet which is tugging Neptune around, and he said, I think it must be right here. And he pointed his telescope out there, and what do you think he found? He didn't find anything, because he was looking in the wrong place, and his calculations weren't very good. And so then he looked a little bit more, and he searched around, and he couldn't find anything, and then he died. And then he left the search to someone else after he died. And can we have the next slide? And he hired a guy named Clyde Tombaugh to use this telescope here. Next slide. Next slide, please. And what Clyde Tombaugh did is he did this neat trick that you can do in the solar system. And he said, well, okay, so you know the constellations. What's the name of one constellation? Orion, right, okay. So Orion rises in the east and then sets in the west. And Orion was named by the Greeks. And so we know that the position of the stars of Orion hasn't changed. It's been that hunter position for thousands of years. And so the Orion stars, they rise and then they set, but they don't change their position. And so anything which does change its position, its shape in the sky, has got to be not a planet, but a star. Or not a star, but a planet or a comet or something like that, moving through the solar system. And so what Percival Lowell did, he did this little trick. And he took a picture of the sky, and then he came back a week later and took a picture of the sky again in the same place, and then he looked for anything that moved. And he did this all over the sky. And so what he did is he saw this picture here, and then he went to the next picture, and he went, I'll show you two of the pictures which he took here. And if you look at them, there's one tiny point in here which moves, and you can just barely see it. I'll highlight it here for you. Right there, and it moves to right over here. And this is the discovery image of Pluto, in fact. And so this is when Pluto was discovered in 1930. Now at this time, we couldn't really know very much about Pluto. All we could tell, these are the discovery images. And all we could tell is that Pluto was moving very slowly. Moving very slowly means that it's a long way away from the sun, out beyond Uranus and beyond Neptune. If it's a long way from the sun, that's very, very cold. They couldn't tell how big it was. They couldn't tell how much mass it had. They couldn't tell if it had moons around it or anything like that. All you can tell is that it's moving slow, it's a long way away, and it's cold. And so even in the best telescopes they had, they couldn't really study it more to really figure out exactly what was going on with Pluto. Now in the next century, in the next couple of decades, there were some more studies of Pluto. And so these are pictures that were taken in 1976 at the U.S. Naval Observatory in Flagstaff, Arizona. And an astronomer there, Jim Christie, was looking at Pluto, and he saw there was this little blob on the top. And you can see that, you can see kind of that blobby area on the top of Pluto there. And then he came back a couple of days later, and this blob had moved down to the bottom. And what he proposed is that this blob was actually a moon around Pluto. And it was correct, it was the moon called Charon, which is going around Pluto. It has an orbital period of 6 days. So it's just like our moon goes around once a month. Charon went around Pluto once every month. Next slide, please. And so we now knew in 1978 that Pluto had a moon going around it. Next slide. Next slide, please. In 2006, astronomers using the Hubble Space Telescope discovered 2 more moons named Nix and Hydra go around Pluto, and you can see them there. Next slide. Then in 2011, astronomers using the Hubble Space Telescope again found one called Kerberos. And then next slide. In 2012, I was part of the group that discovered the moon named Styx. also going around Pluto. And it's a little bit hard to see up there, but it is in that circle, and I promise you that moon doesn't really exist. Next slide. Okay, so to put Pluto in context here, Pluto is the smallest planet in the solar system. In fact, it's, next slide. It's about the size of India, and the other moons are the size of some of the other smaller islands and so forth. In fact, even the Styx and Kerberos are about the size of Kathmandu, just maybe 10 kilometers across on Styx, the smallest moon, about the size of KT. Next slide. So up until, studying Pluto with the telescope, you can only see so much. So I showed you the best pictures of Pluto we've ever taken from the ground or from Earth. And even in those best pictures, Pluto really just looks like a blob, right? So from those pictures, this is about what you can tell. This is about everything that we knew about Pluto before we sent a spacecraft out there. We know its size. And so this is an actual Hubble picture of Pluto. This is on the upper right there. This is a picture of Pluto and its moon named Charon. And so we can tell its density by how fast its moon takes to go around it. We can tell a little bit about its composition. We know that Pluto has an atmosphere. It's a very thin atmosphere. Its atmosphere is about 1 lakh times thinner than the atmosphere on the Earth. And it has these 5 moons going around it, but it's just a blob. On this surface here, we can't see any body, any craters or impacts or mountains or anything like that. Next slide. Now, what do we guess that would be on the surface of Pluto? We can guess a little bit because we know that Pluto is small. If Pluto is small, and we know it's cold because it's far away from the sun. So if it's cold, does it have oceans on it? Probably not, because they're all frozen. If it's small, it's probably cooled off also. Just like a small glass of chai is going to cool off a lot faster than like a really, if you have like a 10-liter jug of chai, it's going to cool off a lot slower than a small one. Pluto's a small planet, so it'll probably cool off quickly from when it was formed. What we would expect is there's a lot of impact craters. Impact craters are caused by asteroids and comets hitting the surface. If we look at almost anything in the solar system, it's covered with impact craters. This is a picture of the moon, and you can see the moon has impact craters all over it. In fact, it's almost saturated with impact craters, meaning if you put another impact crater on there, then you sort of get rid of an impact crater that's below there. And the Earth has impact craters too. This is one that's in India called the Lunar Crater. And we have these impact craters all over the Earth. Now, on the Earth, a lot of these impact craters, they get eroded away. And that's because they get filled with rain, and we have erosion and wind and things like that. So on Earth, the impact craters slowly go away. On the moon, or we'd expect on other planets, most other planets, the impact craters stay there for a long time. So if you look at Mars, you can see impact craters all over the surface. If you look at Mercury, it's covered with impact craters, like this. In fact, you can tell how old the surface is by seeing how many impact craters are on that. So what we would expect is that Pluto, well, it's old, it doesn't have an atmosphere, it doesn't have plate tectonics of volcanoes, so you would expect it to have lots of impact craters on it. Does it have that? Is that what it looks like? We'll come back to that once we get to the new pictures of Pluto. Next slide. So you can study Pluto from telescopes from the ground. So this is a telescope in the Himalayas. This is the Himalayan Chandra telescope in Ladakh. And it's one of the highest telescopes in the world. Let's see. Now you could just make a mirror that was like 3 meters, 4 meters, 10 meters across. But when you get to build too big a mirror, 2 problems. One is too expensive, because you can't really build a mirror that's 100 meters across. And 2, it just becomes too heavy and it breaks, because if you try to build a single piece of glass that's 100 meters high, it's just going to fall apart. It can't support its own weight. So you can't just build a telescope that's as big as you want. But there's a little trick that you can do in the solar system to see a planet in high resolution, even with a small mirror. Next slide. And next slide. And next slide. And one more, next slide. In a solar system, you can take a small planet, or a small telescope, and you can fly it to Pluto. Cool trick, huh? So what we did with our spacecraft is we have a small telescope about this big, and we took it to Pluto. Next slide. So this is our mission. This is the New Horizons spacecraft. This is the NASA spacecraft, which we launched in 2006 on its way to Pluto. Next slide. So this is a $700 million mission. It's paid for by NASA, the National Aeronautics and Space Administration of the US. And this is just a robot. It does not have any people on it. So we didn't send any life to Pluto. We didn't send any people to Pluto. And that's because it's If we would have sent people to Pluto, it would have cost hundreds and hundreds of times more, and it would have been much, much slower to get there. We wanted to build the smallest spacecraft that we could, so we could get out there quickly, because Pluto is a long way away. It's 6 billion kilometers to get out to Pluto. And you might think that what we want to do is land on Pluto. We would love to land on Pluto, but it turns out that to go out to Pluto, you have to go there really quickly. In order to land, we'd have to slow down, and it takes a lot of fuel to slow down. Pluto's so small that it doesn't have much gravity, so it can't slow us down either. So what we had to do is fly to Pluto, take some pictures, and then keep on going, because we're going too fast to slow down. Next slide. So if you look at our spacecraft here, it's pretty simple. It basically has 3 main parts, which it has its cameras, it has its radio, and it has a big battery on the side. And if you think about it, what do you all have with you that has a camera, radio, and a battery? Y'all have your mobiles, right? So next slide. So we're basically sending this nice smartphone to Pluto. Now we have a much bigger battery than the smartphones do, and we have a much bigger camera, but it's the same basic idea. We're clicking pictures, and we're hitting send, and then we're transmitting them back over the radio link back to the Earth. We save them on board and then send them back. We have a big telescope about this big across, but it actually only has 1 megapixel of resolution. That's because it's very dark out of Pluto, because you're far away from the sun, and that's the best resolution for us, where we have the big pixels. Next slide. So this is a diagram of our spacecraft here, and so we have a bunch of different instruments on here. We have over here we have an ultraviolet spectrometer, which is looking at the atmosphere of Pluto. We have an infrared spectrometer, which is looking at the composition of the molecules on the surface of Pluto. Ignore this for now. I do not have the 3D model with me. I'm sorry. Down here we have the what's called the student dust counter. This is an instrument which was built by students at the University of Colorado in Boulder, by undergraduate and PG students. And what they did, it's a piece of film that detects dust particles when they strike the spacecraft. You think of space as being empty, it just has the planets in it, but it actually has dust in it. Dust is made from leftover dust when the solar system was being built. And we actually hit about 1 dust particle per day during our journey all the way out to Pluto. So 9-year trajectory out to Pluto, we hit about 1 dust particle per day. Here's some other instruments that detect the radiation environment, the charged particles from the sun, and how that interacts with Pluto's atmosphere. And then this is our main imaging camera that takes black and white pictures, just monochrome pictures of Pluto, but at high resolution. Next slide. And next slide. So this is we instigated the idea for having a mission to Pluto in 1990 from the scientists. It took a long time arguing our case with NASA to get the funding from NASA to actually build this mission. And there was a competition between different groups that wanted to build the mission. And I was with a group called the Southwest Research Institute, and our mission was selected for flight and funded in 2001. Then we got it ready. We had a couple of years to launch it, or to prepare it and build it and test it and launch it. And then we launched in 2006. Next slide. Now here's a couple of slides of constructing it. This is constructed in different parts across the US. This is at the Johns Hopkins University Applied Physics Lab in Maryland, just outside of Washington, D.C. And you can see here, this is it's an aluminum structure here with some carbon fiber on top. And this is the main spacecraft bus, the main body itself. Next slide. This is one of the spectrometers. This is the infrared spectrometer. This is looking for, as I said, the molecules, the composition of the molecules that make up the surface of Pluto. And so you're looking for ethane and methane and water ice and carbon dioxide and things like this. And so why is this woman, why is she wearing a bunny suit there? Think about this. This is trying to detect the composition. What about if there's hair or fingerprints that get inside the instrument? We take our instrument up to Pluto, and then we say, "Whoa, Pluto looks like it's made of hair and fingerprints." So everything is designed to keep our instrument clean, so we can get the best science observations at Pluto. Next slide. So here we are putting the wiring on the spacecraft. When I say we. My role is not in doing hardware construction, although I was doing some of the calibration. We have a lot of technicians who are doing the actual assembly of the spacecraft. Next slide. Here we are putting the antenna on the top. So this is a 2.5-meter antenna which communicates with the Earth. Next slide. I like this slide. This looks like the doctors and their baby out there. Next slide. And we have to spin the spacecraft to balance it, because much of the time when the spacecraft is flying to Pluto, it's stabilized like a gyroscope. So you spin it because it's most stable that way. Next slide. So here's the team here. Our team is led by Dr. Alan Stern at the Southwest Research Institute. He's what's called the principal investigator. He's in charge of the whole mission. This mission is funded by NASA, but is not actually run by a NASA center. It's not actually run at one of these centers that you've heard of, like the Jet Propulsion Lab or the Kennedy Space Center or Cape Canaveral. NASA funds this mission, they oversee it, but it's actually built at our labs in Colorado and elsewhere. And so this is one of our meetings. I'm way in the back here. There's a huge team here. Now, not all of us are scientists. There's maybe 20 or 30 scientists on the mission. And then there's a lot of electronics technicians. There's a lot of IT people. There's a lot of safety engineers. There's a lot of writers. There's journalists. There's program managers. There's financial managers. And so there's opportunities for all sorts of different people of different educational backgrounds to be involved in missions like this. In fact, it wouldn't work if we didn't have help from people of all sorts of diverse backgrounds on this mission. Next slide. So we started this mission. When I started this mission, next slide. Next slide, please. I was in Colorado, right here. Parts of the mission were built at the Southwest Research Institute in Texas, and then we drove it out to the East Coast, where it was assembled, and then we took it down to Cape Canaveral, which is the same place that the space shuttle launched from in Florida, out here. Then we sent it off into space right there. Next slide. So here we are in early 2006, assembling the launch vehicle at Cape Canaveral. And so this is the launch vehicle. That's just a fancy name for rocket. And so this is the rocket right here. It's basically filled with fuel. And in fact, that's almost all what it has in it is fuel. The main fuel that it uses is kerosene. Kerosene, like paraffin, like gasoline, it's the same thing. Now in space, when we're flying, or even in the high atmosphere of the Earth, there's less oxygen. So we actually have to take along our own oxygen in order to burn this fuel. And so it's about half oxygen, liquid oxygen, very cold. About half oxygen and half kerosene that we take along with us. And then on the side here, these are other booster engines, and these burn a solid propellant, which is a little bit different. And so this is the nose cone, and the spacecraft is right in top, right up here. Next slide. And so this is our rocket here. And what's interesting about it is that it doesn't burn the whole way to Pluto. In fact, it's a little bit like a bowling ball, you know. So we burn the rocket for about 40 minutes. And then we turn it off. In fact, then the rocket disconnects. And at that point, it's like a bowling ball, or it's like a paper airplane, that once you push it, it keeps on going to its destination just by gliding, just by an unpowered cruise through space. And so it's like the bowling ball. You toss it here, and as long as you point it in the right direction, it's going to get to where you throw it. Now we can cheat a little bit, because we have little tiny engines on it that we can steer it just a tiny bit. If we get a little bit, we want to change our course a little bit to correct its motion. It turns out it's actually pretty easy to navigate through space, because we know exactly where all the planets are. We can see their positions pretty well. And if you want to navigate, through Kathmandu, there's a lot more obstacles. There's potholes, and there's trucks, and there's all sorts of obstructions in the road and so forth. So you need to make thousands and thousands of corrections with your steering wheel as you're driving through town here. But driving through space, we make about 3 corrections, maybe 5 corrections on our entire trajectory, because the laws of physics are very, very well understood. It's just gravity. It's just gravity from the other planets, and that's all we need to worry about. Next slide. So here we are a couple of days before launch. We're rolling out the rocket to the launch pad. Next slide. And we have lots of friends and family assembled here. Over here is the, you might have seen this like in the movie Apollo 13. This is the vehicle assembly building. This is where they built the Saturn V rocket and where they serviced the space shuttle at Cape Canaveral. And our launch pad is right over here. And so we're about 10 or 15 kilometers away from it. Next slide. It says do not feed the alligators, because there's a lot of dangerous animals out there. Next slide. And lots of people with their cameras waiting for the launch. Next slide. And here we go. So we did our countdown, and our spacecraft went up into space on the rocket successfully. Next slide. This is one of the writers and scientists on the mission. It takes about 30 seconds for the rocket to go into space beyond the clouds where we can't see it. Next slide. It's one of the geologists on the mission. Of course, we've been working on this building the spacecraft for the past 5 years or so it's a very emotional time. Next slide. This is one of the artists and animators on the mission. Next slide. And hit the space.
T-minus 1 minute and counting.
So this is the launch. So these are lightning towers.
Third stage is go. Roger.
Turn it down a little bit. So this is just so the spacecraft doesn't get hit by lightning, because of course we have a lot of rocket fuel there.
Minus 40 seconds. Stable at step 3.
So you can see the steam coming off. That's actually very cold condensed water coming in from the liquid oxygen. These are the booster rockets on the side.
Dallas lock. TS reduced for launch. Roger. 25 seconds. Status check. Go Atlas. Go Centaur.
T-minus 18. 15 seconds. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. Plus 15 seconds. Everything continues to look good as the Atlas V vehicle climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system. T plus 35 seconds. T plus 40 seconds.
See all of the solid rocket boosters and the main rockets burning there. And in a little bit, the solid rocket boosters are actually going to run out of fuel, and then they get jettisoned off. They get thrown off of the main vehicle. So we're following this from telescopes on the ground and actually from some chase planes as well. SRBs, so the solid rocket boosters. And so we're accelerating this whole way. We're going above the speed of sound now. And we're flying east, so we're flying over the Atlantic Ocean. That's because it's a safe area. It's a protected area.
Pluto, RD-180s throttling up to 100%.
RD-180s, those are our main rocket engines. They're actually made in Russia.
T plus 1 minute, 45 seconds. Everything continues to look good.
1, 2,
boosters have just jettisoned.
5, solid separation looks good.
So these solid rocket boosters, they go off, they fall into the ocean. Then
main stage still running fine. T plus 2 minutes and counting.
Start ground system securing. Vehicles currently flying at 33 nautical miles.
So about 33 nautical miles downwind from where we started over the Atlantic Ocean. Next slide. Now this is the fastest spacecraft that we've ever launched from the Earth. This is, if you look at the Apollo missions, next slide. Next slide. So if you take a Ferrari and try to drive that through the streets here, you probably have some obstructions here, but maybe if you try to drive to the moon, you can do it in about a year if you're driving full speed that time. Next slide. Apollo 11, next slide. Took about 4 days to get to the moon. Next slide. New Horizons, next slide. We took about 9 hours to get to the moon. And we didn't do any studies of the moon. In fact, we passed its orbit after 9 hours, but we didn't intersect with it. But the reason why we're going so fast, this is why we do robotic exploration, because this is a very lightweight spacecraft, and we didn't have to take on humans or food or oxygen or anything like that. So we have the smallest spacecraft that we can build on top of the largest rocket that we can buy. Next slide. And so we launched in 2006. Next slide. And then we had a cruise all the way out to Pluto. We passed Jupiter after 1 year in 2007. And then we had 2008, 9, 10, 11, 12, 13, 14, 15, until we got out to Pluto. Next slide. We just took a straight line trajectory. We passed Jupiter. Jupiter gave us a little bit of a gravitational slingshot, a gravitational flyby, so we got a little bit of extra speed from Jupiter that cut off a couple of years of our trajectory. Next slide. I'm going to show you a couple of pictures of our flyby of Jupiter, because they're some of the best pictures we've ever taken of Jupiter. Next slide. So this is the highest resolution global image of Jupiter ever taken by any spacecraft, and you can see the great red spot of Jupiter here. You can see what are called the zones and the belts, which are essentially just different atmospheric structures in Jupiter. The great red spot is a storm which has been at Jupiter for 400 years. It's the longest lived storm that we've ever seen in the solar system. Next slide. Also at Jupiter, we see the rings of Jupiter. This is one of the things which I study, is the rings of Jupiter. And so Jupiter itself is way over here, and these are rings which orbit it. We all know about the rings of Saturn, but Jupiter has rings too. They're very faint, they're much smaller, much harder to see than Saturn's rings. But they're very interesting. In fact, you can see that there's moons going within the rings here too. This is a moon called Adrastea. There's another one called Metis. And these moons provide some of the dust which is seen in the rings. Next slide. Also on Jupiter, we can see it has a moon called Io. Io is a moon which is very easy to see in a telescope. For instance, the Astronomical Society has a small telescope, an 8-inch telescope, with a mirror about this big. And with a telescope like that, or even smaller, you can very directly see the moons of Jupiter. It has 4 moons called Io, Europa, Ganymede, and Callisto, which you can see very easily. Now, Io is one of the most interesting moons in the solar system because it has a lot of volcanoes on it. And these volcanoes change the surface of Jupiter very dramatically. So we went past with a spacecraft called Galileo in 1999, and then 8 years later we went past with New Horizons. And you can see, here there was nothing, and then later there's this volcano that just popped up over here. Again, in the northern region, there's nothing here, and then 8 years later there's a volcano right there. Next slide. And so you can see that the structure on the surface of Jupiter has changed so dramatically. It's kind of like if you, you're here, and then suddenly, Mount Everest disappears. It's just dramatic changes to the surface of the planet. Next slide. Over just the course of a couple of years. And we actually saw one of these volcanoes being made in process. And so this is a short little movie where you can see of the fire fountain coming out from the volcano, coming out on the surface of Io, and changing it in the process. Next slide. So we had a 9-year cruise in order to get out to Pluto. During this time, we weren't just sleeping, we were busy. And the reason we were busy is we just had one shot to do everything right at Pluto. So we spent all this time, so the way this encounter at Pluto is going to work is that we basically have one day of observing. Because before that, Pluto's a long way away. It's very small. Remember, we have a small telescope, and our spacecraft is moving very fast. So even a week before Pluto, it's sort of too small to do a lot of observing. So our best observing is going to come in that 24 hours right around when we get to Pluto. And it takes us about 4 hours to receive a message back and forth, and then another 4 hours to send a message back to Pluto. And so it takes us about 9 hours round trip. And so we don't want to just, we can't tell the spacecraft, oh, this part looks interesting, zoom in on it. And we can't be interacting with the spacecraft like that. What we have to do instead is program the spacecraft ahead of time. And we have to say, okay, look here, then scan over here, then take 3 pictures down here, then look at the right side over here, and then send all those images back. And so we program it ahead of time, take about 1,000 or 2,000 pictures of the surface of Pluto, and then send them back to us. So we spent this 9 years basically optimizing our scientific sequence, trying to guess what would be the most interesting scientific parts of Pluto to look at, trying to figure out how do we optimize our science so we can take the most number of pictures and make sure with a high degree of certainty that nothing's going to go wrong with our sequence. And we want to practice it, we want to rehearse everything on the ground, rehearse what we can in the spacecraft, because we just have one chance to do it right. And if we screw it up, we're not going to get another spacecraft from NASA to do it again. Next slide. So my involvement in the mission, throughout the mission, before launch, I was involved in designing or calibrating and testing our infrared spectrometer. That was the one that's looking for the composition of the surface of Pluto. During cruise, I was involved in writing a lot of tools that we used to plan the observations. And I was planning a lot of the observations of rings and of dust and of moons, because we don't know if Pluto has rings, or we didn't at the time. But what we want to do is search for rings, because it would be really exciting if Pluto has rings. We know that there's rings around Jupiter, Saturn, Uranus, and Neptune. And we thought maybe Pluto might have rings as well. And then at the encounter, I did a lot of the observations of looking for the rings and searching through this data to see what we could find. Next slide. Now, when we first launched, when we were selected for launch, we told NASA that we wanted to go to Pluto and Charon, because at that point we only knew of one moon that was going around Pluto, and that was its moon called Charon, its largest moon. But we now know that there's 5 moons going around Charon, because we discovered more using Hubble Space Telescope around the time we launched and then during our cruise. And so, on the one hand, this is kind of exciting because this means that that we have 5 moons for the price of 1, so we get to explore more science, and that's really great. But on the other hand, that's a little bit dangerous. Next slide. Next slide. A little bit dangerous because here's the deal. Our spacecraft is going really fast. It's going about 30,000 kilometers per hour. And when you're driving your car or on a motor, if you hit a piece of dust, it's not a problem, no big deal. But if you're going 30,000 kph and you hit a piece of dust, it could actually destroy your spacecraft. In fact, just something the size of about 1 millimeter or less could destroy your spacecraft at that speed. And so we wanted to be sure that when we went to Pluto, there wasn't going to be a dusty environment there. Now, we thought Pluto would be good, but then we started discovering all these moons. And, I showed you that picture of Jupiter's rings. And wherever you had the rings, you had moons at the same time. Rings are just made out of dust. The ring is just a dust cloud. It doesn't have gas in it. It's just a dust cloud. And so we thought, well, maybe if we have all these moons here, maybe there's a lot of dust clouds going around Pluto as well. And so maybe, we had this idea when we were halfway to Pluto, we thought maybe it's actually dangerous to go to Pluto. Maybe we can't actually do our mission because we're going to lose our spacecraft. And we thought maybe what we want to do is instead of going right through the center right very close to Pluto right here, maybe instead we should fly past over here. We wouldn't take as good at pictures, but at least we would have a safe spacecraft, and we would be able to travel through the system without being destroyed. That was our thought. So next slide. So we did a lot of studies to try to figure out whether it would be safe or not. We can't search for a millimeter-sized dust grain. We can't say like, oh, is there a millimeter-sized dust grain 100 million kilometers away? Like, we can't do that. Our telescopes are not that good. But what we could do is we could look and see if there were clouds of dust grains that we should avoid. And we did that using telescopes from the ground. We did that using the spacecraft itself, and we did that using computer modeling, where we tried to figure out are there regions of Pluto where dust grains would be stable, kind of like pile up in space. Next slide, please. And so we spent a couple years on this of the cruise. It's very tense, and what we concluded in the end is that it's a pretty safe system to go to. Thankfully, because we had our spacecraft going there, and we really wanted to go to Pluto. We didn't want to divert it. We would have diverted if we had to, but what we concluded is that it was going to be safe without dust, and that turned out to be correct. Next slide. That we returned and released from Pluto, and so you can see this is kind of like the Hubble Space Telescope image that I showed you of Pluto before, where you can kind of see Pluto and Pluto and Charon here as blobs. There's a blob there, and there's a fuzzy blob there. They're in color, but they look about like the Hubble images. Next slide. So that one was taken in April of 2015, about 3 months before we actually got to Pluto. Next slide. And here we have, now we're getting closer. This is later in April, and you can actually start to see, it's not a blob, but you can see little white and dark patches on the surface of Pluto. Now this may not look like much to you, but this is hundreds of times better resolution than historically we've been able to see from Pluto, where we just see Pluto as 1 pixel, essentially. Here we have 100 or so pixels on the surface of Pluto. Next slide. And here we have a movie of Pluto and Charon orbiting each other. In fact, you can see they orbit around the center, a point at the center, they're kind of both orbiting each other. Next slide. Okay, so here we are in June. We're about 2 weeks out from the encounter. The encounter is going to be July 14th, 2015. Next slide. Next slide, please. Can I have the next slide, please? And then next slide. And then every day we're getting closer and closer as we get new images. Next slide. Until the images stop. So hold there. And so on July 4th, we were transmitting data to the spacecraft. In fact, we were transmitting the final commands that tell the spacecraft how to observe Pluto, the final list of images that we wanted it to take. And without this list of images, the spacecraft would fly past Pluto without observing anything, because we wouldn't have given it instructions yet. And we were transmitting the signals to Pluto, or to the spacecraft, and we listened for its response, and we heard nothing. The spacecraft had vanished. And so we, sometimes this happens, like if the antennas are broken. And so we called up the receiving station, which was in Spain, to see if the antennas were broken there. Nope, the antennas are working fine. And so we thought, well, maybe if there's weather, maybe if there's a monsoon, that'll block the signal from getting to the antennas on the Earth. And so we checked the weather. Nope, there's no monsoons, no rain. So that hadn't happened. And so we searched around to find out where our spacecraft was, and we couldn't find it. About 3 hours later, we found it on a backup frequency. Next slide. And the spacecraft had somehow rebooted itself. Somehow it had a failure, and it had stopped transmitting, and it woke up. We basically turned it off, and it turned itself back on. And it woke up, and it was confused. It had been programmed, when it's confused like this, to automatically phone home. But then it didn't know what to do after that. So next slide. So it was put in what's called safe mode, and that means that that's what it does when it's confused and woken up. But this is very, very scary for us, because we had just 1 week before we were supposed to get to Pluto, and suddenly our spacecraft is broken and not responding. Next slide. Now, luckily for us, we had the best person in the world to do spacecraft operations, and this is our mission operations director, Alice Bowman. And so she ran all the engineers who were on our team, and it's her job to keep the spacecraft healthy, to figure out what was going on with it, and to figure out a fix to it. Next slide. And so we spent about 3 days trying to figure out what was all going on with the spacecraft and trying to fix it. And so, so this may happen to you sometimes. If you're out with a friend and you get separated from them, and you get out your mobile and you're like, "What's up? Hey, what's up? Where are you? And are you okay?" And they message back to you, and you go back and forth a couple of times until you figure out what's up. We couldn't do that with our spacecraft. Well, we could a little bit. But every time we send a message to the spacecraft, it takes 4 hours to get there, and then it has to think about it, and then it takes 4 hours for that signal to come back home. And so it's about 8 hours every time we send a signal back and forth. We just have about a week till we go to Pluto, and so we don't want to have too many 8-hour back and forth transmissions. So in fact, we did about 3 back and forth transmissions. We figured out what was wrong with the spacecraft, and then we figured out what had caused the problem. And what caused the problem is we were actually overloading the processor on the computer. We were asking it to do too much. And so we had to upload new software to the spacecraft. This is like updating the software on your operating system on your Android, but on your mobile, and then like pulling the plug out when it's halfway through that upgrade process. And that's what we've done with our spacecraft. So we had to reprogram it, test this reprogramming, upload new software to it from 6 billion kilometers away, and hope that it worked. And we were very careful, and we did a good job of it. And 2 days later, we were back on track. So our mission operations group did a fantastic job there. When I say we, I'm including everybody in the team. I'm a scientist. I'm not involved with actually doing the operations for the spacecraft, but they're an amazing group of people. Next slide. And so 2 days later, we're getting images back of Pluto again. You can see we're getting closer and closer, and we're seeing more and more of the surface at higher resolution. Next slide, please. July 9th, we're getting closer and closer. Next slide. July 12th, we have 2 days until we get to the encounter. Next slide. Okay, so what's going to happen at the encounter here on July 12th? So we get close to Pluto at about 3 o'clock in the morning. That's when we receive our highest resolution global image of Pluto. In other words, where we take one picture of Pluto where the whole globe fits in the sky in the image. So and then it takes 4 hours to send that down. We receive that about 3 o'clock in the morning. Then we get our closest approach to Pluto at about 8 o'clock in the morning. And then during the whole day, Pluto, the spacecraft is observing. The spacecraft, it can only do one thing at a time. It can't observe and send data to us at the same time. It's just like when you're clicking photos of someone. You can't click photos and then send them at the same time. So we programmed the spacecraft to click the photos and then save them on board. And then over the course of the next months and months, it sends them down. But we also wanted to monitor the spacecraft and see if it was okay. So we actually programmed it at one time to send images back to us and say like, okay, here's how it went. I took the images. It was successful or it was not successful. Next slide. Okay, so here's the morning of the encounter. And this is the student dust collector team. Here are some of the students, and this is the group from Discovery TV right here. Most of the scientists are staying in one hotel outside of Washington, D.C. Next slide. And here we are in the, next slide please. Here we are in the conference room, and it's 6 o'clock in the morning as we are waiting to see this first global image of Pluto as it's released to our team. So do you want to see the image of Pluto?
Yes, sir.
Okay, next slide. And next slide. Whoa. So this is so exciting. So this is our first global picture of Pluto at high resolution. So this is what we've been waiting 9 years to see. And what we found, wait, have it quiet a second. What we found here is really exciting because we found that it doesn't look like the moon. The moon has craters all over it. And what we find is a couple of craters here and there. But what we find is it's not uniform. It's very, very different on different parts of the surface. It's very heterogeneous, we can say. So you have this kind of reddish part up here, and you have this dark brown part over here, and then this white part here. And then, next slide. Next slide, please. And then we have this heart-shaped part of it, because we love Pluto, and Pluto loves us too. Next slide. So in fact, if you compare these images with Pluto, with the moon, so here we have the moon, and you can see the moon has craters all over it. It's covered with craters. It's billions of years old. So it's kind of like, you have this old truck which you've been driving through the streets of KTM for the last, 30 years, and it's beat up, and it has, dents and crashes all over it, right? So you can kind of tell how old a truck is by seeing how beat up it is, right? And if it's brand new, you think it's pretty new. But here, what we saw at Pluto was kind of a truck that looked like this, where it looks like it must be an old truck because all of the planets were made 4.5 billion years ago, but it's been freshly resurfaced. It has a brand new coat of paint on it because you see no impact craters. Well, here's one impact crater right here. Maybe there's one right there. But basically, it's a surface which has not been hit by impact craters for very long at all. So it's a much, much younger surface than we expected. It's much more, and that means something has been repainting or resurfacing Pluto that we don't know what it is. Next slide. So here's our science team as we're looking for these first pictures, just as they're coming down. Next slide. And looking at this first global image. Next slide. And what I love here is, these are geologists, and they're just like geologists would do as they're hiking through the Himalaya, looking for ravines, looking for mountaintops, looking to find new geological features and try to explain what happened to them. Next slide. And saying, okay, here's a ravine, here's a crevasse, here's a coulomb, and so forth, and what sorts of geology could make these processes in the Himalayas, or what sorts of processes could make this geology on Pluto's surface. Next slide. And so we spent a day looking at these images, this global image of Pluto, and seeing what sorts of geology is going on there, and totally reprogramming our minds, because we expected it to look something like the moon, old and battered. Instead, what we found was something which was young and different and surprising. And so, the spacecraft, meanwhile, is observing Pluto the whole day. It's not talking to us, because we've programmed it just to observe Pluto. And so by 8 o'clock in the evening, we're waiting in a conference room as we're excited to hear from the spacecraft. We programmed it to phone home one time. So here's some of the science team up here. This is the spokesperson of NASA right down here. Keep an eye on him. Next slide. And so we wait in this conference room. You can see on the TV that we're watching, we're not all in the Mission Operations Center, but we're watching the mission operations on a closed circuit here. And so here we have Alice Bowman right there. And next slide. And I have a short little video here, so press the next slide there. Okay, and let's crank the volume up a little bit here. And so we're just waiting for this signal to come down.
Okay, we're in lock with carrier.
In lock with carrier means that we're receiving a signal from the
Stand by
spacecraft.
for telemetry.
We haven't received any data yet. So she's talking with the radio operators in Spain.
Mission Operations Manager Alice Bowman, Carl Wittenberg, Mission operations team next to him.
So we're going to analyze the signals that are coming down. Keep your eye on this guy back here.
Are you safe?
Deep Space Network.
He's
And
at the head
lockout
of time.
symbols.
So that's the first step. Including data.
Okay, copy that. We are in lock with telemetry with the spacecraft.
So that means we're getting data down there. Well, we don't know what these data say yet, but at least the spacecraft is live and healthy.
See a lot of green numbers now.
Which healthy.
Copy that. Nominal for power.
So now she's going through all the subsystems of the spacecraft.
Mom.
Asking them how they are. Really.
Mom, this is thermal on Pluto 1.
Go ahead, thermal.
Thermal reports nominal, all temperatures green.
Copy that. Thermal is nominal. All temperatures green. Okay. PI, Mom on Pluto 1. We have a healthy spacecraft. We've recorded data of the Pluto system, and we're outbound for Pluto.
That's the rest of us observing in the conference room next door. Next slide. There's that NASA spokesperson again. Usually he's like that up top, but it's a pretty exciting time. So, next slide. This is one of the postdocs on the mission. She's studying the geology of the surface of Pluto. Next slide. Next slide. And what's remarkable about this, our navigation team is amazing. 9.5 years, 6 billion kilometers, and we got there 1 minute early. So the laws of physics, the laws of physics are going to be right. We can understand the solar system pretty well. And we can navigate our spacecraft there pretty amazingly well. Next slide. Okay, so this is like the photo I showed you before, but what we've done is stretch the colors, just stretch the saturation in Photoshop, essentially. So you can see the differences on the surface of Pluto. And you can see different regions. Like up here, this kind of yellowish, reddish region is one kind of ice, maybe methane ice up here. Over here we have, this is kind of like smog and dust over here. It's a little bit like the smog that you would get in the city. Nitrous oxides and things like that, things which are made in the atmosphere sometimes and then fall back down to the surface. Pluto does have a very thin atmosphere. It's about 1 lakh times thinner than the atmosphere on the Earth, but it does have a thin atmosphere. Over here you see very kind of purplish regions like this, which is maybe like the ethane ice. And then over here we have nitrogen ice in this heart-shaped region right here. And so there's all these different regions. There's kind, on the moon all looks gray. It's all mixed together. Mercury all looks gray. It's all mixed together. And we would expect to see something like that on Pluto. What we didn't expect to see is these really sharp boundaries between these different regions, like we do see. And so it means there's a lot of geology and physics that we don't understand that's going on Pluto. Next slide. Now, if you zoom in here we're zooming in on the heart, this region that we call Sputnik Planitia. And what we see here is, so this is about 30 kilometers across, so Kathmandu is going to fit in, here or so. And what we see is that, well, if you go to a glacier, we think of ice as being solid, solid liquid gas, and the ice is solid. But we know that glaciers actually flow slowly through the mountains, so we have ice falls. And nitrogen ice works the same way. It looks like ice, but it's actually soft, and so it can flow. And in fact, this nitrogen ice is flowing, and it looks like it's sort of turning over, kind of like when you boil water. If you're boiling the chai, and then the water turns over, right? And so it looks like the same thing is happening with this nitrogen ice. Now, it's not turning over every second, like it does when you boil a chai, but it's turning over about every maybe 50 years or 100 years, slowly convecting. And that's because, with chai, that you put the heat source below, and then heat rises up. Same thing happens with Pluto. It looks like there's a heat source at the core of Pluto, and that's causing some energy to leave Pluto and come out through the surface, and that's turning over these surface particles. Next slide. So here we have these mountains on Pluto. these ice mountains. Like right here, you can see how tall these mountains are. This is 4 kilometers high, and you can tell by the shadow here. And so these are mountains which are almost as high as Mount Everest, or half the height of Everest, but on the smallest planet in the solar system. Next slide. So here we have these mountains again, poking through the nitrogen ice, and then we have a couple of impact craters right over here. Not too many though, but you can see maybe where the nitrogen ice has poked in there. So it's this brand new, fresh surface where it looks like, maybe the reason why we don't see any craters here is because they get filled in by this nitrogen ice, like that one is right there. Next slide. So this is Charon right here, Pluto's largest moon. And what you can see about Charon, if you zoom in here, well, the first thing is you see there's a lot more craters here. On the bottom, it's not heavily cratered like the moon, but there's a lot more craters. Up top, there's not very many craters, but down here, there's a lot of craters. You can see this big hole over here. We don't know what's happening there. And you can see the top is all painted red. We don't know what's happening there. Maybe this is smog, which has been carried from Pluto through space and then landed on Charon. Next slide. Actually, go back. So you can see this big crack here going across the whole distance of Pluto. It kind of looks like the Grand Canyon in the United States, but instead of being a small crack, it goes across the whole globe. A big crack, if you've done baking, that sometimes you can get a crack as your bread expands in the oven, or sometimes as things contract, they can get a crack in them. So next slide. It's kind of like that happening on Charon. So it looks like Charon used to be maybe a little bit larger, and then it contracted as it cooled, and this made this big crack on the side of it. We don't see this anywhere else in the solar system, not a crack that's this big. Next slide. We saw the other moons going around Pluto as well, Styx, Nix, Kerberos, Hydra. And we looked at their rotations. We didn't take high resolution images of them because our Pluto was our main goal, but we did image the entire system. Next slide. And so we made up maps of the entire surface of Pluto, and naming them not just after astronomers and scientists from our country, but named after astronomers, scientists, and explorers from every country in the world. And as many of you may know, we're very happy to call the tallest mountains on Pluto. We have Norgay Montes right over here, just down the road from Hillary Montes as well. So Nepal has its place in the surface of Pluto. These are we were extremely happy to have the support of the Nepalese people in naming these features. These features were named in collaboration with suggestions from people all around the world, and they're in the process of being approved as the official names that will be used forever on the surface of Pluto by people from around the world. Next slide, please. And here we go, Norgay Montes again, right over here. The tallest mountains on the surface of Pluto. Hillary Montes over here. And what's really dramatic, I mean, it's great to see these Nepalese mountains here, but it's also great to see it, just the contrast on the surface of Pluto, where you have these really, really mountainous regions here, just like the Himalaya, next to these flat plains, where this is just really smooth nitrogen ice right over here. You can also see the layers of the atmosphere. It's really interesting to see these atmospheric layers. Sometimes you see these layers in the Earth, but Pluto's atmosphere is so much weaker than the Earth's atmosphere. We were really surprised to see all this structure on the surface of Pluto. Next. So just a couple more images here. This one's just too cool not to show. This is where we're looking right at the edge of Pluto, where that heart turns into the edge of Pluto. And so you can see that you can see some mountains and craters on the edge here. And then what we're going to do is pan down here and scroll down. So next slide there, please. And so this pans down. You can see craters here. You can see craters filled with black in here. What look like cat scratches over here. You can see the contrast between ice and other kinds of ice or darker rock there. Then we get into this really bumpy terrain right here. And then smaller bumps. Things like canyons and crevasses. Looks like going through the mountains here. And then suddenly we get to the beach, and it looks like we go into these large frozen nitrogen plains right here. And where you can see these contours and these bumps, maybe sand dunes, maybe sun pits on the surface of these nitrogen plains on Pluto. So it's so interesting to see all of this geology. Some of this geology is similar to what we see on the Earth, and some of this geology is like what we've seen nowhere else on the Earth before. Next slide, please. And so my predictions for Pluto, back in 2012, is that I thought Pluto would be boring. I thought it would all look the same. I thought it would look like the moon. It'd be old and cold. And what we found out, next slide. Next slide, please. Is that all my predictions were completely wrong. And that's cool. I mean, if your predictions are right, like that's great. You can clap, whatever. But if your predictions are wrong, that's much more interesting because that's when you actually learn something. So we're learning a ton about Pluto. Almost everything that everybody predicted about Pluto was wrong, and that makes it the most exciting place to go to. So we're really excited to be so wrong about everything we guessed. Next slide. And what we found on Pluto, just to wrap it up, is that we thought Pluto would be old. It's not. It's young. Pluto was made at the same time as everything else in the solar system, but it's been resurfaced. It has this brand new coat of paint on it. And something is keeping that going. Some process has given it that new surface, that new coat of paint. And so there's still some warmth inside Pluto. It hasn't cooled down and frozen completely, even though it's so small and so far away from the sun. We don't know exactly why that is. Pluto's made up of all these kinds of ices. It has water ice on it. We didn't look for life on Pluto. Pluto's really just too cold and to look for life. It's not a good candidate. There's other places in the solar system that we're much more interested in looking for life, even though Pluto does have water ice on it. Water ice turns out to be pretty common throughout the whole solar system. And Pluto clearly, is a planet from the standpoint of geology. There's just so much stuff going on it, so many physical processes. Next slide. Okay, we visited Pluto in 2015. It took us about a year to transmit all our data, and now we've gone on a couple of years. What are we going to do next with our spacecraft? Next slide. So we have this. Let's look at this map of the solar system. I put it up at the beginning. So we started here. We went past. We intersected Pluto out here, and now we have the spacecraft that's flying out here because we didn't stop at Pluto. What are we going to do with it? Should we just turn it off? Should we just ignore it? What should we do? Well, we came up with the idea, we have this great spacecraft. Let's see if there's anything else that we can fly past out here. And we used the Hubble Space Telescope to try to search for some more objects in what's called the Kuiper Belt. The Kuiper Belt is this list of bodies out here, cloud of bodies. And we looked for objects in the Kuiper Belt out here. Next slide. And we actually found one. We found a couple of good candidates, and we found one which is right close to our path. And so we could actually turn our spacecraft a little bit so we could go very close to it. And this is an object. It's called Ultima Thule. And these are stars right here. And this is our object. And it's moving just like when we discovered Pluto, or just when Clyde Tombaugh discovered Pluto, moving next to the stars. Our object, Ultima Thule, is slowly moving next to the stars as well, just like this. Next slide. And so it's on our path. We're going to fly past it. We have about 6 months until we fly past it on January 1st of 2019. And so this is just one of thousands of icy Kuiper Belt objects in the outer solar system. And we're going to study it just like we studied Pluto. We're going to see what it's made of, what its history of, whether it has any moons going around it, whether it has rings going around it, these sorts of things. Now, it's pretty hard to study it because those pictures, these are the best pictures that we have of this body. We don't really know its position. We don't really know its size, its shape, and it's really hard to plan our observations of Pluto because with our spacecraft, if it's really big and right here, it's a different observation than if it's really small and right here. So we're doing a lot of studies right now to try to figure out exactly where it is in space and how to observe it exactly. Because we want to go past it. We want to know exactly where it is so we can direct our spacecraft there. Next slide. Can I have it quiet a second, please? So here we are in last summer. We went to South Africa. We had actually a very fortuitous event, which is in South Africa. And we had the solar eclipse that passed across every year or so. There's a solar eclipse. And it turned out last summer there was a solar eclipse that went across America. And what happens in the solar eclipse is the moon blocks out the light from the sun. In this case, for a couple of minutes, about 3 minutes, as the moon slowly passes in front of the sun, and the sun disappeared. Now we have eclipses with other stars, and too, the moon can pass in front of other stars, or in fact, Pluto could pass in front of other stars. And this time, we had a case where our Kuiper Belt object named Ultima Thule passed in front of a very distant star. Now this is a very, very faint star. And and it was only being blocked for 3 seconds, but we knew that this was going to happen, and we knew that if we observed this very carefully from the ground, we could learn a little bit about the size and the shape and the position of our Kuiper Belt object, Ultima Thule. And so what we did is we sent about 50 or 100 astronomers down to South Africa, including myself. We went down to South Africa, we looked, we set up our telescopes like this one right here. This is a 16-inch telescope, it's about this big. We set it up to look at the sky, and we wanted to do a 3-second observation where we looked at exactly about 5 o'clock in the morning on July 4th, 2017, to see this star extinguish for about 3 seconds. And by doing that from enough places, we could figure out exactly where and how big our Kuiper Belt object was. So next slide. So we did that successfully. We got a lot of constraints on the size and the position of our object. We're doing some more observations from Senegal in Africa in about a month from now. And so all these are coming together to get our observations of Ultima Thule settled down. So we're going to do a great set of observations over the New Year's holiday. I know that I'm going to be busy. I'm going to be at the lab with my colleagues studying the Kuiper Belt. And going to be really excited to get the first observations of this close-up Kuiper Belt object down. We're going to be. So I hope that all of you follow that as well. And next slide. Our spacecraft is going to, after going to visit the Kuiper Belt, it's going to keep on going, just like it doesn't slow down at Pluto, it doesn't slow down at the Kuiper Belt, it keeps on going. And maybe another 100 years, it's going to leave the Kuiper Belt. Next slide. In another 50,000 years, it'll leave the solar system. Next slide. In another 5 lakh years, it'll do a distant flyby of the closest star, maybe Alpha Centauri or another star. And we're not going to be operating for the whole time. I mean, most of our team is not going to be surviving until 500,000 AD. But and the batteries and the power source and the fuel is going to be depleted long before that. But we are going to, the spacecraft itself will continue outwards because nothing's going to stop it. The gravity's not strong enough to pull it back. Next slide. So here's our team, here's our Mission Operations Center, and thank you so much. So anyone in front have questions here? Yes, please. If you just say your question. Yeah. Sure, thank you. Well, so the question is, how did I get so fascinated and into astronomy in the first place? Some kids are really interested in doing astronomy from a very young age. I wasn't like that. I didn't have a telescope when I was a kid. I wasn't always outside learning the constellations or anything like that. But I had a summer job when I was in as an undergraduate studying. Doing astronomy at a college, and then I met some people who were actually observed and interested in observing Pluto. They were scientists, and from this summer internship, I'd never done astronomy before, but I thought, wow, that's really fascinating because the solar system is interesting because it's a long way away, but it's also kind of close. You can send a spacecraft out there and visit. It's not like a black hole that you can never explore. You can never get there. And so the solar system is just sort of neat because it has this combination of being like mysterious and far away, but also tangible enough that you can walk on it and you can pick up a chunk of it and so forth. And so then I finished my undergraduate studies, and I was thinking of what I wanted to do for postgraduate studies, and I applied to a lot of different postgraduate programs. Most of them rejected me because I wasn't very well qualified. But one of them accepted me, and I thought, wow, this is really great. And so I took the opportunity to do that. I went to the University of Colorado for my postgraduate studies, and really got excited in studies of the solar system from that point. And so it's a lot of different countries across the world have space agencies. I know that Nepal is in discussions of starting a space agency for starting exploring the universe and exploring the world around us, because it really builds the connection between humans and the outside world. I mean, everybody on Earth can see the sky. Everybody on Earth can see the planets. There's something which is not political about it. It's just sort of scientific knowledge, and it's knowledge for all of humanity to expand our horizons, expand our worlds, and that's what's just so exciting about it. Please. Do we have the microphone here? Can we hand it around?
The question answer round. We would like to honor you. Southwestern State College would like to honor you with the token of love. So I would like to request Dr. Rajan Keshi and the Southwestern State College team to honor Dr. Dhruv with the token of love.
Please.
Thank you so much, Dr. Hendro. We have also a certificate of association for you. Before handing over to you, I'd like to recite this certificate of association. It is our great honor and pleasure to present Dr. Hendro in recognition of grateful appreciation for your highly esteemed contribution and extraordinary devotion in the promotion of science and technology as a senior science fellow. Your precious support, invaluable advice, and admirable suggestion will be highly appreciable to enhance in the field of science and technology in the world and in Southwestern State College. Society, and for your cooperation and support, I'd like to honor you as well. Please come forward, Suresh Bhatta and Manisha, come together here. And I'd like to request our campus chief. And I also thank you, the great energetic and music team of NASA. And please come forward, you can go, Susan, Swarat, and I don't know, please come forward. Yeah. It was a great support from the very beginning. Where is Susan? Susan, come over. Ladies and gentlemen, you don't believe that these young and energetic people are doing so much for developing astronomy in Nepal. Accept the token of love. for Dr. Henry Group. For clear message. Okay.
So our next session is the question and answer session. To moderate the session, I would like to request Mr. Suresh Vatrai. After the question and answer session, we will have a group photo session with all of you outside the hall, and then we will have tea, coffee, like refreshment session. During that session, and I already mentioned that we will be taking group photo of a particular group of students and school and team. So please be in the group, so we will take a picture together. So for the question and answer session, I'm handovering this mic to Suresh, and I would like to say thank you.
Thank you, Manisha, for inviting me again, and thank you, Dr. Henry, for this wonderful presentation. I think I should look for my career in planetary science. No. So in fact, we plan to do something because one of our scientific advisory committee member is doing this planet hunting, and he got featured in Nagarik National Delhi and also got awarded by Nepal government with Young Scientist Award last year. So with this small note, the floor is open for the question and answer. So since we are 20 to 30 minutes late from our schedule, so for next 20 to 30 minutes, we'll try to take questions from you, and Dr. Henry will try to answer your queries as much as possible. So if there is any questions, please raise your hand, and when you say your questions, please say your name and your institution. If you are studying in school or college, say your grade also. So it will be easy for us to answer. If you are from class 8, XYZ school, please say that. So it will be easy for us to answer, I think. With this small note, the floor is open for the question.
My name is Mohit Panta. I'm from Nepal Mega College. I'm +2 student, and I would like to ask you some questions. New Horizon mission passed Pluto, and there are a lot of extraterrestrial life maybe in our universe, and New Horizon may meet some such extraterrestrial life if there is possible. And does NASA is serious that about the possible catastrophe that extraterrestrial life can cause on our Earth, or they can make us friends?
Yeah, so NASA is very interested in searching for extraterrestrial life, and NASA and other space agencies, the European Space Agency and the other groups spend a lot of money, hundreds of millions of dollars a year or so, looking for life on Mars or using SETI for radio signals and so forth. And so Pluto just turns out not to be the place to look for life, because life is complex chemistry. And that we get the most complex chemistry at warm temperatures and in liquids. Like, we think that life on the Earth originated probably in the ocean, or maybe on the beach, where you have lots of liquids, lots of energy, lots of heat, lots of chemical reactions. And Pluto, even though it's warmer than we thought it would be, Pluto is still quite a bit colder than what we think are the conditions to create life. And so there's other places in the solar system, like Jupiter's moon Europa, or Saturn's moon Enceladus, or Mars, or maybe a moon called Titan, where we're much more interested in focusing on looking for life.
Small note again. So if you make your questions precise, I think it will be easy for us to answer. I think to Dr. Henry. So we have another question. Please introduce yourself.
Namaste. My name is Ishika Bowden. I'm from St. Mary's College. I recently completed my high school. And my question is the fueling system of the New Horizons spacecraft sufficient enough for us to like escape the Kuiper belt or escape the solar system or reach the nearest star?
Yes. So the question is our velocity enough for us to keep on going? And it is, we're going fast enough that we're going faster than what's called the escape velocity of the sun. And then the escape velocity of the sun is, I forget, let's say 20 kilometers per second. We're going about 30 kilometers per second. And so we're going faster, and the sun's gravity will never ever pull us back. So we will leave the sun, and we'll go on to the other planets and stars out beyond that.
We have another question.
So can you explain more detail about phone home signal?
About what?
Phone home signal.
Oh, the phone home signal. Okay, so this is the movie that I showed at the end. And this is what happened is the spacecraft can't send a signal to us at the same time as it's observing, because it can only point in one place at a time. And so what we did is we programmed it to just send us one signal, just to tell us. A phone home signal is just like, I'm okay or I'm not okay. Basically just that. And so we programmed it to do that. It just took about 15 minutes for it to send that signal with all the data, and then it proceeded on with its observations. So that's what the phone home signal movie was about.
We have one question. It's a little bit different. They want to ask on InSight mission.
My name is Videndra Lama. I'm from Caswin Valley College. Recently, I have given a board exam of plus 12, and I want to ask about InSight mission, which was launched just before 1 month. May, there was on May 5, and I think it will land it maybe November 26. Am I right?
Yeah, that sounds about right. Yeah.
And could you tell us about some information about that InSight missions?
Yeah, you bet. Okay, so the InSight mission, this is a NASA mission, and it's a mission to Mars. And InSight is basically on the Earth, you can study a lot about the Earth's interior by listening for earthquakes. And of course, sometimes earthquakes have devastating consequences, as we're all familiar with here. Sometimes earthquakes also can be, earthquakes on the other planets can be used to tell us about the interior of the core. And they can tell us about, when there's plates moving back and forth. And they can tell us about how much energy is contained in the heat in the core, and so forth. And so the InSight mission is actually studying the earthquakes on the surface of Mars. Mars has, is not as geologically active as the Earth, so there's not as many earthquakes. And we don't have, for instance, the plate tectonics on Mars that caused a lot of the earthquakes in the Himalaya. But we do have smaller we think that there's smaller earthquakes that are on Mars, or we call them Marsquakes. And so the InSight mission is specifically designed to look for Marsquakes on the surface of Mars. So it has a couple of very similar seismometers to what you would use in monitoring stations on the Earth, but we take them to Mars. And so it will land on the surface of Mars. And it's not a rover, it doesn't drive around the surface, it doesn't sample the atmosphere, it's really focused just on understanding the seismology and the Marsquakes on Mars.
Namaste. I am Devra Sriyan from Siagar Higher Secondary School with my friends and teacher. I have a question for you. Is it possible? It is life possible in Pluto?
Pluto is too cold for life. The coldest life that we've ever seen is about -20 Celsius in Antarctica. Pluto is about -250 Celsius. So no life that we know of live on Pluto. Do we have any questions from up top? Please.
Hello. Hello, Dr. Henrik.
Hello.
It's me, Sabana from Southwestern College. I'm studying here in 12th grade. And my question is quite ordinary. And it's why none of the scientists, or I mean people, have not stepped on the other planets yet?
Yeah, good question. Okay, let me tell you. Basically, so we have stood on the moon. We've sent astronauts to the moon. And right now, most of NASA's exploration of the solar system is using robots rather than using people. And the reason is actually very simple, that people are really expensive. And if we were to send a mission even to Mars, it costs about 100 or 1,000 times as much to send a mission to Mars, to send a human to Mars, as it does send a robot. So we can send 1,000 robots, just like the InSight mission. We can send 1,000 InSight missions to Mars for the price of sending one human to Mars. And so we can just do so much more with NASA has a limited budget, just like any government agency has a limited budget. And NASA has decided that it's much more efficient to send robots than it is to send people. Now there's some things that people are really good at. And there's something, and it's also really, kind of exciting because we have a human connection with seeing Neil Armstrong walk around on the moon. So, there's an excitement there too. But there's also a balance between what's expensive and what's not. So there's a lot of interest in sending humans either back to the moon or to Mars, and I'm sure that in the next decades that will happen too.
My name is Cecil Gimire and I am from Southwestern School. Could you please tell me what are the factors that change the surface of Pluto?
What are the factors that change the surface? So let's see, Pluto gets changed. The main thing that influences Pluto's surface will be things like asteroids and comets hitting it. That will make impact craters on the surface. We also have some influence from the atmosphere because there's some smog which is created in the atmosphere, which then causes nitrous oxides to fall down onto the surface of Pluto. We also have a lot of chemistry from the sun, which causes chemical interactions on the surface, and that changes the chemicals on the surface. And then we also have some heat from the interior, which is coming out and makes kind of like geothermal events, kind of like the geothermal activity you might see in like Iceland or Greenland with volcanoes happens in Pluto as well. So those are the main things.
Hello sir, this is Rahul Kumar Misra from Tichandra Multiple College. I am doing a bachelor in physics. I have 2 or 3 questions for you. I am quite interested in Voyager 1st, 2nd, and Cassini, and this one, New Horizon. So how does this trajectory of these all spacecrafts are planned? And you said that Jupiter gravity assists, increases the speed of the New Horizon. How it all are done?
Yeah. Okay. So how do we plan the trajectory of a spacecraft? It turns out it seems like it would be complex. It turns out it's very easy because if you've taken a physics class, how many people have taken a physics class? All right. So you know 2 equations. You know F equals ma, and you know G equals mm, or F equals gmm over r squared. The equation of Newton's first law, and you know the equation of gravity. And these 2 equations put together is all you need to navigate through the entire solar system. And I'm not exaggerating when I say that. Those are the only equations that are used. And so if you know where all the planets are at the start, and if you put a spacecraft that's moving, that spacecraft is carried around by its own momentum and by the force of gravity from the other planets. And if you put a trajectory there, and then you say, then you can predict, if you know where your spacecraft is going, you can predict exactly where it's going to be. And then if you want to change its orbit a little bit, you can change its orbit by doing a small burn of an engine, and then you will know exactly where it will be. So it's actually very, very easy to navigate through the solar system, just using the equations of physics.
Hi, Dr. Sir. I'm Abhishek. I completed my computer engineering from IOE Pluto campus. It was a very articulate talk to hear from you about the New Horizons mission. But I was kind of I was surprised to not get any information about the demotion of Pluto as a planet and didn't hear it from anybody, so I'd like to know your views on that.
Okay, let's see. Can we have the projector turned back on? I'll show you a couple of slides on that. Let's move this out of the way. Okay, here we go. The Greek definition of the word planet was a wandering star. If we know anything about Pluto or anything about planets, they're not wandering and they're not stars. Can you go to the next slide there? And so, the word planet has never really been defined until a couple of years ago. Next slide. And hit the next slide there. Yeah, okay, so historically, throughout time, the word planet has meant a bunch of different things. Like sometimes people, this is an old dictionary here, and sometimes people refer to the sun as a planet. Sometimes people refer to asteroids as planets. In fact, scientists still call them the minor planets. Sometimes people refer to the moon as a planet, and so people call everything a different planet. And but no one had really defined it scientifically. Next slide. And so is Pluto a planet? Next slide. So you can make a list of reasons why something might be a planet. Pluto is a planet for a lot of reasons. Like it orbits the sun, and it's big enough so that it's if something is big, it makes a ball. If something is small, it can make a funny shape, like a mango. But if something's big, gravity pulls it always into a ball. And Pluto's big enough to be into a ball. And it has all these moons. It has an atmosphere. We've always called it a planet. So all these argue that it is a planet. But you can also argue the other side, and you can say well, it's not a planet because it's smaller. It has this weird orbit that's more elliptical, more like an egg shape. And it's much more like the other Kuiper Belt objects than it is like a planet. And because it's smaller, and it's icier, and stuff like that. And maybe if we discovered today, we wouldn't call it a planet. So you can say that. And so there's kind of a balance here. Next slide. And so there's a group called the International Astronomical Union, and they tried to make a definition of the word planet a couple of years ago. And in fact, why don't you just hit the next slide button a couple of times there. They came up with this definition. Let's not go into the details of it, but this definition is not actually very good because they say, if you read it technically, it says, the Earth is not a planet, and Jupiter's not a planet, and other planets beyond the Earth beyond the Sun aren't planets either. And so there's lots of problems here. Next slide. Next slide. So this one fails for a lot of different reasons. Let's hit next slide a couple of times. Next slide. Next slide. And so I think a lot of it really just boils down to size. Next slide, please. And if we see something which is really big, if we see Jupiter, we say of course, oh well, Jupiter's obviously a planet, right? And if we see a dust particle, next slide. A dust particle, 1 millimeter across, is that a planet? Most people would say, no, it's a dust particle, it's not a planet. But what about something which is in between? Here we have Pluto, 1,000 kilometers across. It's kind of like halfway a planet and halfway not a planet. And so where do you draw that line? And it's really just it's a fine line, and it's kind of arbitrary where you draw it. Next slide. And so this group, this is the International Astronomical Union. They had a vote about, in 2006. About whether Pluto was a planet or not. And it seemed kind of funny to have a vote on a scientific issue like that, but that's what they did. And so they voted no, Pluto's not a planet. And but the fact is that that plenty of astronomers disagree with that, and plenty of astronomers call Pluto a planet. And most of the people, for instance, on the New Horizons science team, who know Pluto the most, still call it a planet. Not everybody, but most astronomers still call it a planet. So, I still call it a planet. You can call it a planet if you want to. You can call it, the important thing is understanding, how active it is and what the physics which are going on there. And calling it a planet or not is really much more a question of the words that you use rather than the science of what we've found out there.
Hello, sir. I'm Parvesh Pokhrel from Kathmandu University, Department of Applied Physics. And my question is, close to my friend over there, some of the spacecraft like Voyager and New Horizons, when they are projected far from the end planet like Jupiter or Pluto, do they suffer the gravitational the effective gravitational pull of any other planets, dwarf planets or stars? What are the chances of vanishing of those spacecraft? Or what are the obstacles that it may suffer on its journey?
Okay, so what are the probability that the spacecraft might suffer from a collision with another planet or something like that. Well, it turns out that so space is not entirely empty, because I told you that we have dust particles on the way that we count and so forth. But it turns out space is almost empty. And for instance, one of the things we had to do is fly through the asteroid belt. And you might think that flying through an asteroid belt is really, really challenging because like in Empire Strikes Back, there's a scene where Han Solo is like flying the spacecraft through the asteroid belt. It's really tricky, and they have to dodge asteroids and whatnot. Turns out that the real asteroid belt is much, much easier to fly through. You just fly in a straight line, and you could actually go through the asteroid belt about 1 million times before you have a risk of colliding with anything. And so the odds of hitting something are not very high. The biggest risk to a spacecraft is something like a software bug which turns the spacecraft off. Or sometimes you have hardware failures, not from a just an electronic failure or things like that. But human error is a much, much bigger problem than colliding with something. Yeah, there's no other planets out there that we could collide with. If there's something big enough to collide with, we would see it before we hit it for the most part.
My name is Rajani Shrestha and I'm from Multiple College. I'm a bachelor's level student of science. And I want to ask you that, as you had mentioned, that Pluto's surface has been resurfacing and Pluto hasn't cooled completely, and the convection of nitrogen ice is taking place there. And do you have any initial hypothesis as to why it has happened, why Pluto hasn't cooled completely?
Well, a lot of it we don't understand the physics of ices very well. We understand stuff that is at our temperature, like at, what's the temperature in here? 20 Celsius. We understand how things work at 20 Celsius temperatures, but we don't really understand how ice works at like -200 Celsius, which is the temperature which is at Pluto. And so we kind of have to guess a little bit, and it must be that some of our guesses are really, really wrong. It also might be that Pluto's made of different stuff in its core. For instance, the Earth's core is made partly of uranium, and uranium and other radioactive elements, and those decay and give us a lot of heat, and that's what powers a lot of the volcanoes on the Earth. And it might be that at Pluto, we have a guess for how much uranium is in there, but it might be that Pluto turns out to have more uranium and radioactive elements in its core than we thought. And we don't know yet whether, how it is yet, but those are the sorts of things that we are studying with this data to try to figure out what's going on.
Hi, Emily.
Hello.
I'm the student of physics, MS Physics at Pardon Multiple Campus. And my question belongs to exact mechanism system of fuel in rocket. How is it possible to take fuel along with rocket to travel 6 billion kilometers from
Okay. So here's the thing. Most of in the launch vehicle in the movie that I showed, you saw the solid rocket boosters fall off about 1 minute into flight. It turns out the rest of the rocket fuel tank also falls off about 40 minutes later, 20 minutes, 40 minutes later. And so we don't take most of that fuel along with us. We take a small amount of fuel along with us. In fact, we take maybe 200 kilograms of fuel. So the fuel tank is about the size of this podium here. And we take that along with us. And that fuel is something called hydrazine. It has the equation N2H2. And that's a pretty simple fuel that we can just keep in a aluminum drum that were there. And that's the fuel that we use just to point the spacecraft and change its trajectory in very, very small ways. But most of the fuel gets burned just as we are accelerated to leave the Earth's orbit.
Thank you. I think everyone has a lot of questions with you, so please make sure you write it and send us to our page. So we'll try to make sure that Henry will answer all your questions. We'll take now 3 questions. So
here? Only 3, because it's already 4:30.
Good afternoon, sir. My name is Namna Adhikari, and currently I am studying astrophysics in Central Department of Physics. Can you give me some brief description about how does data
to know how are those data handled or received from New Horizons?
Yeah, okay, so how do we handle the data? So most of the data that we bring down are just simple pictures. They're the same sorts of pictures that you would take with a digital camera. In fact, they're simpler because they're 1 megapixel. So it's just an array of data, sort of 1 megapixel. And so you can actually go to NASA's website, and anybody from any country can go to NASA's website and download all of the data from New Horizons, and you can analyze these data, and you can study them for free yourself. What you want to do to study this is to go to what's called the PDS. It's called the Planetary Data System, and you can search for that online. And these images, it requires a little bit of investment of time to learn how to load the images into your software and how to analyze them and so forth. But you can analyze them without if you invest the time in it, you can study them. We also have some data which is like spectrometry, or some data which is data from the dust detector. And we use different methods to analyze that. But most of the data, by data volume, is or by number of images, is just by pure images, which we just analyze by looking at with our pictures or with our eyes.
Thank you for giving me time to say some questions for you. My question is, Pluto's orbit crosses Neptune's orbit. Is there any possibility of crashing?
So Pluto's orbit and Neptune orbit, is there a possibility of crossing? Good question. Turns out the answer is not really. No, they're locked in what's called a resonance. And so it's kind of like, let's see, it's kind of like maybe like an egg beater, where you have the different time, or like a gear, where you have the tines on the gear sort of intermesh like this, and they don't collide with each other, but they, every time this one goes around, this one goes around, just like that at exactly the same speed. So Pluto and Neptune are going around essentially at exactly the same speed. It turns out it's not quite like that. Pluto's going around exactly 3 times, or exactly 2 times for every time, 3 times that Neptune goes around, but they're close multiples of the same speed. And so they are not going to collide unless something else changes in the solar system. Like unless Jupiter comes in there and pushes Neptune's orbit away, then maybe Pluto will collide with Saturn or something like that. But that's going to be in the much, much long distant future, billions of years. For now, Pluto has been stable for billions of years, and we expect it to be stable for a long time more.
We have a last question for today's session. So anyone who wants to ask a question, please make sure you visit NASA page, and you can write your questions over there so that we can track you back and send those queries to Henry. Okay? So it's not that we don't want to get your queries answered, but we have some time constraints, so everything is delayed. So we also have photo sessions outside. So this is the last questions for today's session.
So this is Sogan from St. Mary's College. I just completed my high school, and my question is, I'm curious about the chariot, the moon of Pluto, as you just said. There is kind of grand canyon kind of thing on its surface, and as you said, it's quite peculiar. I want to know whether any kind of research going out regarding that, and I want to also know that what makes it so peculiar that it exists only on the surface of Carrion and nowhere else in any part of solar system that we are aware of.
Well, we want to know the answers to those questions too. That's what doing science is about. Is we don't, we were baffled by what we found there at Charon. Charon has this huge crack going around the surface, probably something to do with its thermal history, how it has cooled, been heated and cooled over the course of the solar system. And we see some cracks on other planets. Like Mars has a big crack, which is probably caused by water erosion, called Valles Marineris. Some of the other planets, there's a moon called Miranda, which has some big cracks on it, which are probably caused by a collision. Maybe there's some other cracks, on the moon or on Mercury, which are caused by thermal contraction, but they're much, much smaller. They're this part of the planet rather than going around the whole planet. So that's just something we're going to have to be studying and learning to figure out where that comes from. And your guess is as good as any. So if you take up a career into the space sciences, maybe you can be the one to answer that mystery.
Thank you, Dr. Henry, for being with us. Let's give him a round of applause.
Very cool, very cool. So you're physics students here, yes? Okay, cool. Which, and how old are you? What level? Second year high school. So, okay, cool. So it's like great. It's like standard level. Yeah, and so, wow, so this is very nice to be able to do the physics experiments here. Yeah. And so, very nice. Very nice lab. Okay, so you can do the motion here, and this is for doing, what's this for? Oh, this is resistance also? Yeah. It's a beautiful, beautiful lab. It's so, it looks like a brand new lab. Yeah, that's great. Very nice, very nice. And the beautiful mountains out there too. Wow.
कति फटाफट हिँडेको सर पनि
Oh, it looks like a really, really fantastic new lab. Fantastic.
Excuse me, hello, sorry. उसलाई रूपालाई खिच्ने भने खिच्दैन मेरो मोबाइल
Awesome. Group photo.
Let's take a team
group photo. Yes, please, please.